All right. Assalamualaikum warahmatullahi wabarakatuh and good afternoon, everyone. So thank you again for joining us. So this is actually the third session that we have for the postgraduate sharing session. The topic today will be a bit more physics as well. We have Mr. Muhammad Al-Habbash, a PhD student at School of Physics. So he basically will share about the modeling optical responses of a multi-layer thin film via polynomial approach. Honestly, I don't really know much about the topic, so I'm going to learn this as well from you. So there is actually about 5 outlines that Mr. Muhammad are going to go through. Should I call you Muhammad or should I call you Habbash? Because Dr. Yun keep on saying that your name is Habbash.
Yes, 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 yes.
Is
It
it
is correct.
Habbash or is this actually Muhammad? So Habbash is
Yes,
your
yes,
name. Okay.
yes, yes.
Because sometimes for
Thank you.
Arabic the name is a bit I mean the way how we say the order is
Pronounce.
actually a bit different, yeah. So Habbash is it?
Yes,
Okay.
yes, it is okay.
All right. So we have like the basic Maxwell's equation for describing interaction between electromagnetic wave and material, polynomial approach for modeling optical electrical responses of a multi-layered thin film, and also type of materials, looses and lossy. And we have implementation of the polynomial model in Matlab code and the numerical experiments and results coming from this wave tensor. So without further ado, I would like to just pass the session to Mr. Habbash. Let me stop the sharing. Okay.
Okay, thank you, Dr. Noor Sakina, and Assalamu alaikum, everybody, and good afternoon. I think it is afternoon now in Kuala Lumpur or in Penang in general. Yes,
Yeah, it's two. Yeah. Don't forget to share your
yes,
slides.
yes. I want to share now my slides. I am very happy to share my work with you and with everyone here in our session, and I welcome anyone who want to join us. And it is a good chance to know about the theoretical physics, my theoretical physics work in the field of electromagnetic in general. Okay. Are you seeing or are you my
Yes, I can see. Yeah, I can see.
yes, okay. Bismillah ar-Rahman ar-Rahim. Today we will talk about modeling optical responses of multi-layer thin film polynomial approach. Here we mean by optical responses the reflection and the transmission in general for multi-layer thin film. So when we talk about multi-layer thin film and we want to simulate it theoretically, we need a mathematical model to represent our work. There are many type or many methods for representing the optical responses. One of them is the polynomial approach. We choose the polynomial approach because it is like when we stack anything like our thin films here, so we can tracing the light when it enter the layer, our layers, layer by layer, and we know every point in the layers what happens with electromagnetic or the light in general. So we want to start, so we want to depend on Maxwell's equation because it is a more general equations that everyone in the field of electromagnetic should use it. Here we see the electromagnetic or the Maxwell equation for electromagnetic to describe the electromagnetic light in general. We have here the four equation. I think it is very famous equations. Here we have the curl, this operator with cross called curl, which means that we have the curl of electric field. This symbol is the electric field. This is the permeability for the vacuum in general. This is the relative permeability for the material, and this one is the magnetic field. Okay, here we have the same thing, but here we have a new symbol, which is the permittivity, and this one is the relative permittivity for the material. Here is the conductivity for the material, and this is the current density for the current which passes through the material. Okay, but if we want to describe the polynomial approach, this equation, the four equation in this form, does not appear to be useful for us. So we want to transfer it or to change it in this form. This form, we have the wave vector. The wave vector, we depend on the wave vector so much in our work in the polynomial approach. The polynomial approach is a mathematical model, which means that we can use it in electromagnetic and in electricity in general. The wave vector is the wave which describes the amplitude and the direction of the wave in general. Okay, and now we have this equation converted to this equation. We have here we have a positive and negative. This positive and negative is depending on the how we in general let us say the electromagnetic used by physicists and engineers. Engineers prefer the positive sign here, but the physicists in general in books and papers prefer the minus sign. So in our work we will depend on the minus sign. But if you open an electromagnetic book, which the author was from the field of engineer, so he will use the positive. So this is for just for clarity. If you want to read books, you should know which type or which sign he used. Okay, these are our four equations here. The same one, the same as the above one, but here the wave vector is up here. And these equations, which is the this is called Fresnel's transmission and reflections coefficient. The T is the symbol for Fresnel's transmission for any layer or for any media, and the reflection, the R is for the reflection for any material, also the Fresnel's reflection. We have here TM and TE, and we will talk about it because there are p-polarized light and S-polarized. The p-polarized is the magnetic polarized light, and here is the TE is the for the if the light is electrical polarized or called S-polarized. Maybe here we can talk about the parameters here. Here we have here the refractive index, and this is a function of angular frequency, and the subscript here, the J is for the layer. So for the first layer we have the, and for 0 it is for the vacuum, and if we increase the J, it will be the, for 2 minus 1 it will be 1, so the first layer, and so on. The same thing for these, but we should know if the light is TM polarized or TE polarized before we simulate the electric or the magnetic field. Here we will talk deeply about polynomial approach. In general, we have two types of polarization, as we said. Here we will show you how we can differentiate between S-polarized or P-polarized. Here we have a TM mode. TM mode means that we have a P-polarized or magnetic field polarized. Here you can see that the field or the light or the electromagnetic field travel in this direction, and we have the incidence angle. Some of the light or the electromagnetic wave will reflected, and some of them will transmit through the media. So here we have the reflection angle, and we have the transmission or the transmittance angle. The direction of the traveling can be represented by the K, which is the wave vector, which represents the direction and the amplitude of the light in general. How we differentiate that this is a TM mode or TE mode? You can see here that we said that this is a symbol for magnetic field. So the magnetic field here is in the Y direction, and here is in for the second medium is in the Y direction, and here also in the Y direction, but the opposite side, in the opposite direction. So the magnetic field here have only a Y component. So it is polarized about the magnetic field. So the light here, maybe the electric field, it change his or its direction from reflection and from incidence and reflection and the transmission here. But the magnetic field is still in the one direction, which is the Y direction. So we said here that the light is polarized about magnetic field. The other side, we said here, we see here, we have the electric field is in the Y direction. For example, this figure is designed to be in the Y direction, but it can be in the Z or in X direction, no problem. But here we choose the Y direction. So the electric field here is in the X or in the Y direction, and at medium number 2, it is also in the Y direction, and here for the reflection, it is in the Y direction. So no change in the, or no more component when the electric field reflected or transmittance through the medium number 2. So this, the way we said that this is a electromagnetic wave, TE polarized or S polarized, okay? TE polarized or TE mode or S polarized, the same name. I want to hear if this at this point is everything is known or everything is clear, or someone want to ask anything? Are you hearing me?
Yes, I can hear you clearly.
Okay, I hope everything is clear now. Okay, or if someone have a question, I can answer before we go deeply in the polynomial approach. Okay, if we want to represent the electric field which travels from light from left to right, from left to right, we have here the electric field or the electromagnetic field travel from the vacuum and pass through these N layers, then come out to the vacuum again. So we want to represent this traveling. So we have here one matrix for the interface between vacuum and the first material or the first layer. After that, the electromagnetic field will travel through this layer, whatever the thickness of the layer, but here we have a beta matrix or propagation matrix for the material number 1. After After that, we have a material or interface matrix to represent what happens in this field, which is the area or the interface between the layer 1 and layer 2 and so on until we reach the N layer. Maybe it appears that it is complex, but if we go up to show you the equations, here we have the interface matrix, and we here have the propagation matrix. For the interface matrix, we have the Frenzel's coefficient, the transmission and reflection, and we represent the interface matrix like this. The J is the subscript for the layer. So if we have the layer number 1, so it will be the matrix A1. And for the layer number 1, when the electromagnetic field travels through it, we have the beta 1 matrix here, which represent the traveling of the electromagnetic field through the layer 1, and the propagation matrix is represented like this. Where is the beta here inside the matrix is defined by the dot or the inner product between the wave vector and thickness. Between wave vector and thickness. So the thickness play a role when the electromagnetic field pass through any layer. So if we change the thickness, then this beta will changes, and this will change everything in our matrix. The transfer matrix for these N layers will be a product of beta matrix and or the propagation matrix and interface matrix, but it will start from the end to start. So we start by propagation matrix for layer number N, then we'll product this matrix with the interface of the interface between layer number N and the layer N-1. So this, if you say here, the product will start from the end to start, or from, if you start with J equal 1, you will find this J will be J plus 1, N minus J plus 1, and it will be N, because minus J plus 1 minus 1 plus 1, it will be 0. So we will start by the propagation matrix, the last propagation matrix, and product it from with the interface matrix between layer N and layer N-1, and this will be this matrix. Or this matrix. This matrix we call it a transfer matrix, which describes the behavior of electromagnetic when it passes from the left to the right. Here we have the conductivity due to this one, sigma here, sigma 1, sigma 2, sigma 3, and so on. This is a conductivity due to accumulated charge. It is not the conductivity of the material. It is the conductivity due to accumulated charge. If we apply a voltage from this interface to this interface, I mean the transverse voltage, then some charges will accumulated here between any adjacent layers, and it will be appear like will be like stacked capacitors. Okay, because every layer is isolated from the other layer, because we will use a dielectric material, so it will be like a capacitors, and these accumulated charge will change the transmission and reflection of the frame cells. Transmission and reflection, as you see here, we have the conductivity. This conductivity is due to accumulated charge. I know that it is somehow complex, but if you concentrate, it will be clear. You should read it more and more to understand. Here we have the equation for the accumulated charge, or the conductivity due to accumulated charge, and you can see that the first sigma, or the first conductivity between vacuum and the first layer, it will be 0, and here for the N layer and the vacuum, it will be 0, because there is no accumulated charge here, because between vacuum and any layer, it will the charge will not accumulate it, so it will be 0. After that, yes, here we can see the equation for transmission and reflection in the of the electromagnetic field for any material. Here we can say something that we change the above transmission and reflection Fresnel's coefficient to be with this formula, because we use a non-magnetic material. When we use non-magnetic material, everything will be more easy. If we use a magnetic material, then the equation will be more complex. So here we have Y and Z matrix, which is the average of this. So when we simulate, or when we try to practice this in lab, we will use the two type of polarization, and we take the average, and we after that we have the Y matrix, and also here we have the Z matrix. The Z and Y matrix is defined to be or used to calculation for transmission for every layers, and the reflection for every layers. Here we have the tangential of the phase. So every transmission or reflection have a phase. So we have a phi t, which means that we have a phase for transmission, and also here we have a phase for reflection. Now, for type of materials, we want to talk about type of materials, because when we simulate the above approach, or the polynomial approach, we have two types of material. We have a lossy material and lossless materials. When we use a lossless materials, then we have the permittivity, the imaginary part of permittivity, and also the conductivity will be 0. So every parameters we use, like complex propagation, when we simulate it, because after we build a mathematical model, we want to represent it or code it in Matlab, for example, or Python, or any program or any language we want. We will use for lossless or for lossy material. For me, I start and coding my code with lossless material, because it is more easy, and we have a result and a published paper. We will show you the results. But now I work on a lossy material. I am about to submit my second paper also for lossy material. For lossy material, it takes me a long time to coding and to build the mathematical model because it is more complex. Also, we have here this table is copy paste from a book which the author is the name of the author is Bozar. I can share with you the book if you want. For good conductor, here we have a more complex and complex equations, or maybe not complex, but some conditions will change because the good conductor is a special case of lossy material, because the conductor is a lossy material also. Here, in general, this is the equation which I reached to when I work on my second paper. Here, the permittivity in general and the refractive index, here the wave vector, and this is the intrinsic impedance. The intrinsic impedance. Okay. Here, for this, for example, I want to start with this. If we have a permittivity with lossless material, then there is no conductivity. This will be 0, and this one will be just a real value. So there is no imaginary value. So it will be like this: epsilon naught multiply by epsilon r, but the epsilon r here is a real part, not, there is no imaginary part, so everything will be easy. And so on. For refractive index, you can see here that this part between brackets here under the square root, this part is the same as this part. So if this part for permittivity be easy or be simple for the case of lossless material, this one will be also more easy and more simple. Also for the wave vector, the same thing. For the intrinsic impedance, the same thing. But if we have a complex number, or we have a conductivity, and the conductivity have real and imaginary part. Also, if we have a refractive or permittivity, relative permittivity with real and imaginary part, then all this equation will be more complex, and we use also the complex calculation or complex calculus or complex mathematics. Okay. I hope at this point the lossy and lossless material you be familiar with, or you can have an idea about the difference between lossless and lossy material, and maybe you now know if you want to start your research. I prefer to start with lossless material because it will be more easy. Any question? Are you hearing me?
Good evening.
Yes, good evening.
Thank you for the presentation. I really enjoy much of what you are saying because I'm almost doing something related to what you are doing. You were talking about lossy material, lossless.
Yes.
So when we're classifying this material, do we say we classify, which of this material do we classify under the lossless and the ones that are generally lossy?
Okay, I want to go back here and to the table here. in general, if we want to test this material to be lossy or lossless material, we will look at the permittivity, because the permittivity have the parts which affect everything or every parameters. You can see here that he said, are you seeing my slide now?
I'm seeing it.
Yes, we have here double dash epsilon, which means the imaginary part of permittivity. Okay, when the imaginary part of the permittivity equals 0 and also the conductivity equals 0, then we have a lossless material. Let us look at this equation again. For this equation, are you seeing this equation? This is the
Yes, I can see that.
Yes, this equation is the permittivity, general equation for permittivity. If we have here a conductivity to be 0 and the relative permittivity here is with 0 imaginary part, then we have a lossless material.
Okay.
Otherwise, we have a lossy material. This is, I think, this is the answer, the clear and good answer to if you want not to search in papers and books. I can sum up my maybe my research or my searching about this point. I can sum up that if you have no conductivity, this one, the sigma is 0, and also the real part or the imaginary part in the relative permittivity equals 0, then you have a lossless material. Okay.
No,
if you have a lossless,
the
you
reason
can see
why
here.
I was asking is because you know, so we classify, sometimes some materials are classified as isotropic and then anisotropic. So when
Yes.
these materials, and then that isotropic material, which now we classify metals and other, I think metals and few this thing. And then when we have the anisotropic, we also have materials classified. So that was why I was trying to get the clarity there. So because I was looking at the lossless material there based on the equation there where you were talking about that is the relativity, if I'm correct.
Yes. Relative permittivity.
Relative permittivity. And then
Yes.
the equation down there. Now, when you expand it, you said the relative permittivity there, if it turns to 0, yes. At this point,
Yes.
very good. Yes, at this point, the general relative permittivity equation, which you have assigned there as epsilon subscript C. Am I correct?
Yes.
Subscript C.
Yes,
Okay,
I
so
called it. See, this is a subscript for to say that it is complex.
okay. Thank you for that. Now I get the whole thing clear because I was trying to a little bit confused there. That's why I have to ask some questions so that will be very clear. Because when you expand the equation there, which you have looked at the small letter sigma up there to be 0, and if it's 0, we now have is epsilon naught by the relative permittivity, which give us the medium.
Yes.
The median.
Okay.
So
Yes.
thank you for that. I'm clear about it.
You're welcome.
Thank you.
Yes, maybe after I finish, I will share with you my ResearchGate profile, and maybe before the end of this year, I will publish my second paper. You can say or you can see my work, and maybe every sample in this session will be more clear, and the details will be in my upcoming paper. And thank you for your question.
Thank you.
You are welcome. Okay, can I continue?
Mr. Habbash, there is a question at the chat box. So what does the real and imaginary part mean in terms of the material's optical response?
Okay, if I understand your question, you ask about the real and imaginary part of permittivity.
Is that what you mean? Stephanie. Oh, okay, yeah. Stephanie, you.
Is it clear, or can I
The question says that in terms of the material's optical response, but someone is actually answered. Can you check on the your chat box?
Yes, as a
Or
chatting.
maybe Stephanie, you can clarify your question.
Okay, you want to chat me or what?
No, someone is already chat in the chat box. Do you know there is a chat box at the WebEx?
I don't know.
You can go at the three button there. There is
Yes.
the three dots. Yeah, three dots in chat.
Yes. Okay. Here. Yes. There is a question.
Yeah.
Real and imaginary permittivity and also the conductivity. I think it is the same question that Abdurrahman. Yes. Okay. I think it is this. Okay. Real. Polarization, real part and absorption.
You have to see from the top. You have to see from the top. You have to scroll up more. So the question is actually
what does the real and imaginary part means? Okay, every material have its parameters which we want. Okay, the real and imaginary in mathematics, we use the principle or the this type of mathematics, which is a complex number, to represent something in our physics. For every equation or for every parameter, the real and imaginary have its meaning. In general, the real part is the part which we can use it, or in general, if I talk about the electromagnetic, the real part is the real part of the electric and magnetic field. But the imaginary part means that there is some attenuation or some absorption. This is due to the type of material, how the material absorbs some power or some energy from the electric or magnetic field or the light in general when it passes through the media. How can we mathematically represent this absorption? So they use the imaginary part to represent this. Okay, I think this is my answer. I don't know if it is clear or not, because to connect or to come from mathematics to physics, this means you should know or understand what the meaning of your equation you use in mathematics and the representation or the physics means. This needs you to look for your equation or for your field in general, because imaginary and real part is used not in electromagnetic, but also in every part of physics we have real and imaginary. Okay, in general, I can say that if we have imaginary part in permittivity, so we have a lossy material. This is my clear answer. So if we have an imaginary part, so we have attenuation. Here you can see in this table, maybe this table is very useful, that the attenuation constant equals 0 for lossless material, but for lossy material, we have a value for attenuation. The attenuation means that the light, when traveling through the material, it will be attenuated. it will be reduced. The amplitude will be reduced. The energy will be reduced. Is it clear now? For Stephanie, I think the question is come from Stephanie. Yes. Is it clear?
Yeah, I think she
Okay.
said okay. Yeah, she said okay.
Okay. Okay. Thank you, Stephanie. Thank you. Okay. I want to continue before the time is going. Yes, here I use the implementation of polynomial model in Matlab code. I use Matlab because I am familiar with Matlab because I work with Matlab from 2003. So I have a good experience in Matlab. So I use Matlab to represent and to simulate the code. And our code here, we call it wave tensor. Okay. The name of, I will share with you the code at the end of this session. Okay. When we use the Matlab, Matlab is short for matrix lab, which means that it is so close to our work because we deal with the matrix. Okay, this is the symbol or the logo for the company of Matlab. If someone don't hear about Matlab, okay. Here our flow chart. You can. I don't want to go deep here, but this is the flow chart for our coding. This is for clarity for me. If I want to debug or to know if I have some trouble or some problem with my code, and also I have to test my code if it is real or not real. So I have to test it. I have 3 tests for my code. One of them for Brewster angle, and the second for conservation of energy, and the third is for critical angle. So I simulate, then I expect to have some figure or some graphs, and if the code give me this graph, then I know that this code is go very well. And if the graph is not as we expect, or then there is a problem. So I test many times my code through my work to be sure if I work very well in coding and represent the mathematical equation very well when I use the Matlab. Okay. Here I want to show you some numerical experiment and result from wave tensor, which is my first published paper in my PhD. Here, this is, if you see here, I have a paper published in Optical and Quantum Electronics journal, and my supervisor, main supervisor, Dr. Muhammad Mahadi Halim, and the co-supervisor, Dr. Yoon. Dr. Yoon, I think you know two doctor or two person here, Dr. Yoon and Dr. Halim. Here I want to show you the result. I don't want to, I can share this paper and you can find it in my ResearchGate profile. I want to show you here the results for my work. Here we can, yes, okay. Here we have a figure for. I use I use 2 dielectric material, which is the magnesium oxide. Okay, and this is the figure for. You can see here the reflection and the phase of the reflection. Okay, for 1 layer. This is the transmission and the phase of the transmission for the magnesium oxide when I have a 0 voltage, or I applied a 0 voltage through the transverse or through the multilayer. After that, I will apply a voltage, 0, 300, 600, or 900 voltage through the multilayer. Here we have 3 layers, which is, or 2 layers, I mean that we have magnesium oxide. After that, I will add another material, which is calcium fluoride. Okay, calcium fluoride. The two material is non-magnetic material and lossless. Okay, lossless material. For the source of numerical or the table or the refractive index for magnesium oxide and calcium fluoride, you can see the reference at the end of this paper. You can know from where I can get this data for magnesium oxide and calcium fluoride, and how can I know if it is lossless or lossy material, how I know it is non-magnetic material, how I know the parameter or the feature of this material. Okay, here we have I want to talk about this figure. We have here the bold one here when we applied no voltage or zero voltage, and after that when we apply a voltage, you can see that you can see here that the reflection is attenuated, or I mean that there is a reduction in the line here. So the bold one when we applied zero voltage, and the last one for 900 voltage. This means that when we applied a transverse voltage through our sample or multi-layer, then the reflection is changed. Also, the phase for the reflection is changed. The transmission also have not attenuated, but it is enlarged or enhanced when we applied a transverse voltage. And this is very easy because we add an energy. Because when we apply a voltage, we add an energy for the material, so the transmission will be more. And also we have just slight changing in the in the transmission phase. This is for 2 layer. Also we have here for 3 layers. The same thing for 3 layers, 4 layers, and also for 5 layers. We have many figures here. We can see this is for 4 layers, and this is for 5 layers. If you notice that for even and odd number of layers, there is a difference between even, because if you find here the 5 layers and compare it with 3 layers, you can find it is very similar. The shape of the reflection and transmission in general is the same. I don't mean that it is typical, but the shape in general is the same. And we will use the even number. I mean that this is for two layers, and for the 4 layers, you can see it also it is the same. So for even number of layers, there is a pattern, and for odd number there is another pattern. Okay, and yes, this is a general for if we apply zero voltage for every, you can see here, for every number of layer, you can see here, these are the even, for the even number of layers, and this is for odd number of layers. You can say that this is a pattern and this is another pattern. Okay, when we apply voltage also, we can find there is a difference, enhancement or reduction. And I think if you want to see the details, you can, I refer you to, I will give you the link to this paper to see and to read more and more and see. This is an appendix which we talked about this before. This appendix is very useful for anyone who want to use a polynomial approach and go deep in electromagnetic, because it is like a base for this paper. Maybe the appendix is have the number of papers or the number of papers for, yes, for the appendix is more than the main paper, because the base is more have more equation and something like this. Okay, let us come here. This is just a link for my paper. At the end, I want to thank you very much for your listening and for your joining us. And here is the ResearchGate, my ResearchGate profile. This is my GitHub. You can find my code for Matlab and some other coding in this link. This is my LinkedIn profile also. If you want to join us or join me or want to share something or have any question, I will be very happy to communicate and to share my knowledge and know also and gain from you if you have, because any person learn more and more when he have more question from others and share his knowledge with others. And thank you very much.
Thank you so much, Mr. Habbash. Any question from
Should
the
I stop
participant?
the okay.
The screen? Yeah, sure. Any question? I believe that you have explained in details.
Okay.
Okay, can you share the links in the chat box? Your links just now. Is it possible?
To share it in the chat.
In the chat, yeah.
Okay, this one or the book. Okay, I will share this everything. Okay.
Yeah.
I maybe okay. I will share this with you. Okay. This is my ResearchGate. Okay. Sorry. Here the chat is yes here. Okay.
You can share all the links. So.
Okay. Now also the GitHub also. And finally, this is my LinkedIn profile. Okay. You can download this paper. You can download this paper from my ResearchGate profile. You can find this paper that I show you. You can find it in my ResearchGate.
Mr. Habbash, there is one question in the chat box.
Yeah.
So I'm curious to know why the even and odd number of layers have different patterns.
Okay. If I want to share again my slide again, can I share my slide again?
Yeah, sure.
Okay. Is it clear now? Can you see my slide share? My slide.
Yes, can.
Okay. You can see here. You can see here when we want to study or use the polynomial approach, we have to multiply the propagation matrix with interface matrix. If we go through one layer or odd number of layers, let us say 3 layers, 1, 2, 3. So we have matrix A1, matrix beta 1, matrix A2, beta 2, again A3, and beta 3. So the number of matrix that we multiply have or play a good role when we change the behavior or the result of the transfer matrix. So if we have two layers, for example, another example, if we have two layers, which means that we have an even number, we have A1 multiply, or I am sorry, we will start when we use this equation. We will start from end to the start. So we have beta 2. We will start here from beta 2 multiply by A2, then multiply by beta 1, then A1. So we have the number of parameters or number of matrix have a pass through two media or two material. If for example, if we say that this one is for magnesium oxide and this one is for calcium fluoride, so the light is passing through just two material, just two material. So we have accumulated charge here between this one, between magnesium oxide and calcium fluoride. But if we have another layer, it will be, you know, this will be a periodic process. So we have magnesium oxide, calcium fluoride, again magnesium oxide, then calcium fluoride, and so on. So the light here, if we have an odd number, will pass through magnesium oxide, then calcium fluoride, then again magnesium oxide. So he will pass through magnesium oxide 2 times, but pass through calcium fluoride just one time, and so on. If we have four, for example, 4 layers, then the light will pass through magnesium fluoride 4 times, because we have beta 1, beta 2, beta 3, beta 4. Beta 4 will be for magnesium oxide and beta 1. Also, the calcium fluoride will be for, I am sorry, the beta 1 and beta 3 will be for magnesium oxide. Okay? But beta 2 and beta 4 will be for calcium fluoride. So you have passed through calcium fluoride 2 times, and which means that it is even number. And for the magnesium oxide, the light will pass through the magnesium oxide 2 times also. So it is even. But if we have 3 layers, then it will be more. I mean that the light will pass through magnesium oxide, the magnesium oxide 2 times, which means that the light will propagate through beta 1 and beta 3, but it doesn't pass through calcium fluoride 2 times. It is just 1 time. It is for for beta 2. The behavior of the light depends on the media and the thickness, and also the incident angle, and also the feature of each material, which means that if it is lossy or lossless, and so on. And also it depends on the number of layers, which means that if we have more number of layers, if it is even and odd, and so on. Is it clear? Thank you, Stephanie. I think Stephanie said that it is clear. Yes. Thank you, Stephanie. I will stop. Okay.
Any other question from the participant? Yes. I'm actually recording the video, so I will upload in the YouTube, and we'll email everyone. So you can actually refer it back. You are okay with that, right, Habbash?
Yes, I appreciate that. It is, yes.
Okay, yeah. So you can share with others who cannot make it today. So if there is no more question, I would like to thank Mr. Habbash. Thank you so much for taking your time, even though you
Thank
are
you.
not at USM right now.
Thank you very
But
much. I
still,
am happy.
yeah.
I am so happy to share with you, and I am miss Penang very much. I want to be with you in Penang very,
Penang is very hot now.
very soon, inshallah. Inshallah.
Inshallah.
Inshallah.
I would just would like to say all the best for your PhD. Hopefully you will complete it soon.
Inshallah. Inshallah. Inshallah.
We
Thank you
will
very much.
have, inshallah, another session, maybe not by November, maybe perhaps December, but I did not have the speaker yet. So if any of you would like to share your research or anything with others, so you can just let me know. So we will arrange another session perhaps in December, because now semester just started, everything just get a bit hectic. So I couldn't really arrange it. So we will have another session, inshallah, in December. Thank you so
Inshallah.
much for everyone. Thank you so much, Mr. Habbash. See you all again,
Thank you.
inshallah, in the next session.
Thank you,
Bye.
Dr. Sakina. Thank you.
Yeah, welcome.
Assalamu alaikum.
Assalamu alaikum.
Assalamu alaikum.
Salam.
Wa alaikum.